Alright, so 9.6, solving exponential equations. This is where we see why we study logs. When you've been in Algebra 1 and Algebra 2, you've learned how to solve equations. If there's multiplication and you want to move something, you divide. If there's addition, you use subtraction. You always use the opposite operation. Well, when we want to solve for an exponent, we can't look at a problem like number 1 and say, well, divide by 3, or what do you multiply by? We need something to do in order to find the exponent. So what we do when you need to solve for an exponent, take the log or natural log of both sides. And it's okay to do that because you're doing it to both sides. But that's when you need to solve for an exponent. In the past, you've just had to know what it was or put it in a table and guess and get close. But now with logs, we can actually find the answer. I'll show you what I mean. If we take the log of both sides, we get the log of 3 to the x equals the log of 52. I haven't done anything wrong here because I took the log of both sides, so I didn't change the equation. Well, we know from expanding that I can move that exponent to the front, and it becomes x times the log of 3 equals the log of 52. Well, to solve for x, I can divide both sides by the log of 3. And so then I get my calculator out, and I do the log of 52 divided by the log of 3. And we're going to round to 1 decimal place, so I get 3.6. So x is approximately 3.6. Let's try it. Let's try 3 to the 3.6 power. Look, I got pretty close to 52. Okay? All right, let's go to number 2. Now number 2, I'm going to rewrite this exponentially. X to the third equals 15. I'm not solving for an exponent here, so I don't need to take the log of both sides. When you need to solve for an exponent, take the log or natural log of both sides. So I'm going to take the cube root. So x equals the cube root of 15, or I could think of it as 15 to the 1/3. I'm going to put that in my calculator, 15 to the 1/3. I've got to put that 1/3 in parentheses. And I get, let's go to 1 decimal place, x is approximately 2.5. I'd say 2.466 is probably a better answer. But if we're going to 1 decimal place, 2.5 is close enough. Alright, now let's go to number 3. E to the x equals 9. Whenever e is involved and you're looking for an exponent, instead of taking the log, take the natural log. So I'm going to take the natural log of e to the x and the natural log of 9. I've done the same thing to both sides. Well, the natural log of e to the x is simply x. If you're not sure why, I'm going to show you up here. Let's make a little thought bubble up here. Natural log of e to the x is the same as the log base e of e to the x. E to what power is e to the x? Well, it's just x. Okay. So the natural log of e to the x is simply x. So on the left side, I get x equals the natural log of 9. And then I go to my calculator. Natural log is right here. Natural log of 9, 2.2 if I'm going to one decimal place. Well, I should write approximately 2.2. It's not exact. Okay? All right. In number 4, we are solving for an exponent, but I always want to try and get whatever I'm solving to that exponent by itself. Like here in number 1, I didn't have anything else in front of that 3. It was just 3 to the x. I want this to just say e to the x, so I'm going to start off by dividing by 5. And I get that e to the x equals 2. Now I'm solving for an exponent, so I'm going to take the natural log of each side because it's involving e. And the natural log of e to the x is simply x. And I can put that in my calculator. Natural log of 2.7. Okay, let's go on to some problems that are more real life problems. It says Susan put $2,000 into a savings account, earning 4% interest compounded continuously. Anytime you have compounded continuously, you use the formula A for the amount equals PERT. Should have learned about PERT in Algebra 2. P is the principal, E is that letter E that's on your calculator, R is the rate, T is time in years. If you need to write that down, this is the principal, that means the amount that you started with. And then R is the rate as a decimal. T is time in years. All right, so Susan put $2,000 into a savings account. That's her principal amount, so $2,000. E, the rate is 0.04, and we don't know the time. But we know the amount. We want her money to double, so we'd want this to be 4,000. So before I can go taking the log or natural log of both sides, I need to get this e by itself. So I'm going to divide both sides by 2,000. And I get 2 equals e to the 0.04t. Now that I'm at this point, I can take, I'm going to do the natural log because this involves e. So I'm going to have the natural log of 2 equals the natural log of e to the 0.04t. Well, this is just going to be 0.04t. Because remember, the base is e. E to what power is e to the 0.04t? Well, this 0.04t equals the natural log of 2. All right, I've got to solve for t. I'm going to divide both sides by 0.04. So let's see, t equals, go to my calculator, I've got natural log of 2, and I'm going to divide that by 0.04. Now, don't take the natural log of 2 divided by 0.04. You can't put the divided by 0.04 up here, because you're taking the natural log of 2, whatever that is, and dividing it by 0.04, and we get approximately 17.3 years. Number 6. If the population of a small town is currently 1,300 and is growing continuously. Anytime it's growing continuously, we're going to use A equals PERT at a rate of 4.5%. Approximately how many years will it take for the population to double? Well, the original amount is 1,300. E, the rate is 0.045. Time we don't know. We want it to double, so that's going to be 2,600. Again, I've got to get that E alone before I can take the natural log of each side. So I'm going to divide each side by 1,300. 2 equals E to the 0.045t. Now I'm going to take the natural log of each side. And remember, this base is E. E to what power is E to the 0.045t. That's just going to be 0.045t equals the natural log of 2. Divide both sides by 0.045. And we'll get our t. So let's see. Natural log of 2 divided by 0.045, 15.4 years.